All right, our next section, oops, I don't know why that happened, is 13.7. Well, let me fix that quick. 13.7, which is surface integrals. So we already did line integrals, and now we're going to move on to surface integrals. So adding another dimension to our integrals there, rather than just along a one-dimensional curve. I guess not one-dimensional necessarily, but rather than just along a curve, we're going to go along a surface. Okay, so your line integrals. We did an integral, which is an accumulation, okay, of a function that changes along a curve. So we could get the total charge along a curve we talked about, or the mass of a wire with negligible thickness. Okay, now we're going to look at surface integrals, which is a function changes along a surface. Okay, so and then reviewing that too, when we talked about line integrals, we had a function we evaluated along the curve. Okay, we call it line integrals. Really, maybe a better term might be curve integrals, but we just call them line integrals. So we have this function that gives us the value of the function wherever we are on this curve. Okay, and then let's do a little, when we do surface integrals, it's also our function. Okay. For line integrals, the domain of that function was a curve. For these surface integrals, cancel. The domain of this function is a surface. Okay. With line integrals, we had a curve defined. I think we did it parametrically mostly. Where we'd have x is some function of t, y is some function of t, and z is some function of t. Okay, we could do a vector equation of the curve too. Okay, for our surface, we're going to have a vector equation R with two parameters. Okay, so x would have those parameters, y would have those parameters, j. And this is, the nitty-gritty stuff. Once you get the examples, it kind of all makes sense. Z is some function. Okay. And uv is, again, those u and v values are within the domain of our function. And then we would do our integral for line integrals, where c would be that curve. Okay, and along the arc length there. So that also, we'd have some function of x, y, and z that was all parameterized in terms of t, remember, so that then we could do, I'm going to run out of room here, that square root of dx dt squared plus dy dt squared plus dz dt squared crossed into the other side there. Okay, and then if you remember too, if f of x, y, z was just 1, then what we were finding there was arc length. Length. Okay. And then over here with our surface integrals, give myself a little bit more room here. We're going to do the integral over surface of f of x, y, z ds, which we learned in the previous section. We can do that surface area as a cross product. So we would do f of r, right, our function here, okay, our surface. F is evaluated anywhere on the surface. Then we do that cross product, RU cross RV, dA. Okay, and we also can do that is the integral over d of f of x, y, and then z, but z has to be in terms of x and y. It's a double integral, so we only can have two variables here. Okay, so we have to be able to define z in terms of x and y. And then we can do, so this is kind of analogous to this one here. Okay, dz dx, dz dy squared, and of course dz dz would just be 1. Okay, and then dA. Okay, and then again, this would be like your z. Okay, and we have something similar too, where if f of x, y, z is 1, then you can probably guess the result is surface area. Okay, and the basic idea of this, okay, basic idea, kind of that, how I like to kind of maybe overly simplify things without getting too much into like the proofs. U and V are parameters. Okay, with UV in that domain of the area. Okay, it's there. U and V get you in your surface. Okay, a small change in U and V gives a patch with area S. Okay, so if we change U and we change V, X, Y, and Z are all going to change. Okay, but we're talking about, again, S is just in 2 dimensions, so you're only thinking about it in like your XY plane. Okay, so if U and V change, then your X and your Y are going to change. Okay, just by a little bit, and they give us like this little patch, right? I mean, you can almost picture it as like a rectangle. X changes, Y changes, then we've got this little rectangle. Okay, the direction of the sides of the patch. So not necessarily like square, not necessarily like right angles. Okay. Because again, U and V, it's almost like that change of coordinates that we did previously in chapter 12, where, it's not necessarily a rectangle brings you to a rectangle. It could be some other kind of shaped surface. Okay. But the directions of the side of the patch are RU, right? These are vectors. And so they're direction vectors, okay, where RU is dx du, dy du, dz du, and RV dx dv, dy dv, dz dv. Okay, so it gets this little patch. Okay, the magnitude of the sides, and again, if you're like, this is a little too abstract for me, totally okay. All right. You can try to read up on it more in your book if you're kind of interested in like the proofs behind it. Most kids really aren't all that interested in this part of it, but I like to get at least a little bit on here. The magnitude of the sides are then RU delta U and RV delta V. Okay. And then the area delta S is the area of that parallelogram, right? We know that the parallelogram with sides defined by vectors is the cross product of the two vectors. Okay, and we can take those constants out. Okay, and then probably know where this is going, right? Okay, and then you find your function. So that's only the second part here, right? We just talked about that piece here. Your function and then is evaluated somewhere in that patch. Okay, function value on S is f of r of, wherever you want to take u and v to be in that patch, right? Okay, and then it gets you your accumulation, right? That infinite sum of all the little patches and all the little function evaluated at the patch. Okay, real basic idea there. Okay, so let's do an example here. Actually, we'll try to get we're going to do one example where we use it with the cross product piece of it. Then we're going to do one example where we do that second piece of it, where we leave it as x, y, and z. Okay, so you can get two different examples to look at. So let me switch some pen color here. I think this is exercise 6 in your book. Okay, they want you to find the surface integral of the function x, y, z ds, where S is cone with parametric equations. X equals u cosine v, y equals u sine v. So we recognize those as the parametric equations of a circle, right? And then, so the cone, cross sections of a cone or a circle, and then z is u. So whatever the radius of the circle is, that's how high we are off of the xy axis. Okay. And we're going to do u is between 0 and 1. And v, you can probably imagine, would be between, well, if we're going to go all the way around, it would be 0 to 2 pi. We're just going to do this one 0 to pi over 2. So we're only in the first octant here. Okay. So again, if you guys can picture this, we would have the parametric equations in x and y give you circles. Okay. From a radius of 0 to a radius of 1, but again, only in the first quadrant. And then the height of those circles is equivalent to the radius. So we'd be down here, and then we would go, I'm going to try to up to here. And we're only in the first octant there, from theta equals 0 to theta equals pi over 2. Okay, kind of a quarter of a cone there. And again, this is at 1 for the height. Okay. All right. So, like I said before, this is all parameterized for us, so it should be really clear that what we want here is to use the form that looks like this. Okay. So, first of all, our function here is xyz. So that's going to be u cosine v, u sine v, v. I'm sorry, u. Okay. RU cross RV. Well, RU u is hold on a second. I should definitely back up here a second because I don't think I was super clear on how you get RU and RV. Because those are the derivatives with respect to u, and then the derivatives with respect to v. What we're doing right there. And I don't. And then that would be 0. Let me back up for a second here because I don't want to. Yeah, I'm sorry. I should have been a lot more specific here. I just kind of glossed over it there, and I really should have focused on that more. Those represent partials, okay? And I kind of just glossed right over it there when I was okay. So this is really important, and I just kind of said, here's what RU and RV are. Okay, so those are your partial. So R, okay, R of UV is U cosine V, U sine V, U. Okay, and then so this, when we do R with that little U, we're doing the partial respect to U, and here we're doing the partial respect to V. Okay, so I apologize there. I didn't really explicitly say that. I just kind of got ahead of myself in my notes. So there you go. Okay, so we're going to do the cross product then. Okay, so the cross product, and then we're going to take the magnitude of it. Okay, so the cross product is, and we got to do the I, J, K. We got to do cosine V, sine V, 1, and negative U sine V, U cosine V, and 0. All right, so when we do our I's, we're going to have negative U cosine V. When we do our J's, we're going to have, let's see here. We're going to have negative, negative, negative U sine V. So we're going to have negative U sine V. And then when we do our K's, we're going to have U cosine squared V plus U sine squared V, which is just going to be U, right? Okay, so then the magnitude of that is going to be, we're going to square everything, so U squared cosine squared V plus U squared sine squared V plus U squared square root. Okay, and then again, this will be U squared. So the square root of 2U squared. So U square root of 2. Okay. All right. Now, it should be clear that when we set up our integral, we want that dA to be polar, right? We want our dA to be a dr d theta. Okay, and we've got an r between 0 and 1. And we've got a theta between 0 and pi over 2. Okay, so we'll do our integral 0 to 1, integral 0 pi over 2. Our function here, so we've got a u cubed cosine v sine v. Okay, and then the magnitude of our cross product, so we have a u and a square root of 2. So I'm going to put the square root of 2 out front, and I'm going to change this to u to the 4th. Okay, and then we're going to have our dr d theta. And actually, you know what? We don't need to switch that because u is already being treated like a radius and v is already being treated like an angle. So I'm going to just leave it as d u dv. This is u, this is v. Yeah, I don't know why I was going to switch it to r and theta. That was silly. Okay, right, we've got u's and v's in here. We wouldn't want to have done that. They already took care of it for us, basically. So then that's going to be dv du. No reason to switch it to polar when it was really already kind of given it to you that way. Okay. All right. Can you tell I'm making these over winter break? My brain is not in school mode. Okay. This is separable for us, so we can do the square root of 2. Integral from 0 to 1 of u to the 4th du. And the integral from 0 to pi over 2 of cosine v sine v dv. Okay. So we're going to have square root of 2 u to the 5th over 5 evaluated from 0 to 1. And then we can do a u sub here, which u sub when we're already talking about u's, right? We don't really like to do that. But u would be sine v, du would be cosine v dv. Okay, so we would have the integral sine of 0 is 0, sine of pi over 2 is 1, and then we would just have u du. So it'd be u squared over 2 from 0 to 1. Okay, so put it all together, and we've got the square root of 2 times 1 over 5 times 1 over 2. So we've got the square root of 2 over 10. And that's your final answer. Okay? All right. So I just want to clarify 2 things that I kind of skimmed over. Again, the fact that these are the partial derivatives, okay, of your surface. And here's your parametric equations of your surface. We made it a vector equation, and then we took our 2 partials, okay? And then the second thing is the reason that I didn't use r and theta is because the way that these are already written is they already are like an r and a theta. You might as well have just an r and theta right there, right? And then this would be r and this would be theta. It doesn't really matter if we're using u and v or r and theta. It means the same thing, okay? So that's why I kind of was like, oh, it makes perfect sense to do it as terms of r and theta, which it does, but don't add more work. They already explained it as u and v. Okay. All right, we're going to do another example. And this one, like I said, is going to use the other format. This is exercise 10 in your book. Okay, and we're going to do the surface integral of xz ds, where s is the surface 2x plus 2y plus z equals 4 in the first octant. So that's a plane, okay? And the fact that they've given this to us, you know, with x, y, and z all related like that, okay, tells us that our better format for this one will be this guy. Okay, it's going to make a lot more sense to leave it like this. Okay, they didn't give us the parametric equations for the surface. Everything's in terms of x, y, and z. It's not parameterized in any other variables. So this is going to be, you know, of our 2 choices, this is one that we're going to want to use for this one. Okay, it's going to help if we can sketch this a little bit, right? So if x and y are 0, z is 4. If y and z are 0, x is 2. And if x and z are 0, y is 2. Okay, so there's your surface. All right. And then when we're talking here, everything, this needs to be z is in terms of x and y. So that would be z is 4 minus 2x minus 2y. Everything in our equation is going to be in terms of x and y. So our integral, we definitely want to have x's and y's. So if we look in our xy plane, right, we have when x is 2, y is 0, 0, 2. We're just taking the same triangle and looking at it here. So this would just be y is 2 minus x. Okay, so x is between 0 and 2, y is between 0 and 2 minus x. Okay, so we can do this. 0 to 2, 0 to 2 minus x. Our function is xz, so it'd be x 4 minus 2x minus 2y. Okay. Dz dx. So the derivative of z with respect to x would be negative 2. Dz dy would also be negative 2. And then plus the 1. And then we'd have dy dx. Okay. So let's simplify this a little bit here. First of all, we're going to take the square root of 5. I'm sorry. We've got 4 plus 1, which is 9, the square root of 9. So we're going to take a 3 out of there. And we'll distribute that x. So we have 4x minus 2x squared minus 2xy dy dx. Okay, so we'll take our integral with respect to y first. So we'll have 4xy minus 2x squared y minus 2xy squared over 2, so just xy squared. Okay, from y equals 0 to y equals 2 minus x. Okay, now we're going to have to do some simplifying there. So we're going to have 4 times x times 2 minus x minus 2x squared times 2 minus x minus x times 2 minus x squared. Okay. I'm going to make, there's different ways we could do this. I'm going to do a 2 minus x factored out. So I'm left with 4x minus 2x squared minus x times 2 minus x. So 2 minus x times 4x minus 2x squared minus 2x plus x squared. And then I have 2 minus x. Just kind of trying to make sure I'm checking my work as I go. 4x minus 2x, that would be 2x minus x squared. Okay, and so that would be 4x minus 2x squared minus 2x squared plus x cubed. All right, so I think what I've got here is the integral of x cubed minus 4x squared plus 4x. Okay, so now I'm going to have x to the 4th over 4 minus 4x cubed over 3 plus 4x squared over 2. Evaluated from 0 to 2. So I'm going to have, let's see, I'll have 16 over 4 minus 32 over 3 plus 8. Everything else would just be zeros. Okay, so I'm going to distribute that 3. So I have 12 minus 32 plus 24. Okay, so I've got 36 minus 32, which is 4. Final answer there. Okay, so again, okay, that's a nice examples here because it's one of each kind. And make sure that you can understand, again, why when given something that looks like this, we're going to go this route. okay? And then y, when given something that looks like this, we're going to go this route, okay? Just make sure that that's clear. All right, I have a couple little examples here. One thing that kind of comes up and that really means more later, doesn't matter as much right now, is an oriented surface. Oops. Okay. If you remember, your unit normal vector, way back to chapter 10, okay, is, oopsie, I think this was in chapter 10, the cross product of two vectors gives you a vector that's normal to them, okay, and then if we divide it by the magnitude, it's a unit normal vector. Okay, so it's what's called a unit normal vector. Okay, if it points out of the surface away from the origin, we have what's called a positive orientation. If it points in, then we have a negative orientation. Okay, and that's all we really need to know for now. Okay, across the surface, we would be able to find all of these normal vectors. In fact, you come up with an equation for the normal vector at any point on the surface if you wanted to. But if they're pointing away from the origin, it's a positive orientation. Towards it would be a negative orientation. Okay. The next thing we're also going to add to this is surface integrals of vector fields. Okay, which we've seen vector fields before. Okay, so F is a, getting all glitchy here, continuous vector field defined on an oriented surface. Okay, so either oriented positively or negative. Okay, with unit normal vector n, then the surface integral of f over s is okay, this, which can also be written as okay, and we could go into the whole proof of why this is the same as this, but for now you're just going to take my word for it, okay? And that's over S, which is also your normal vector, right? So RU cross RV, and then dA, okay, because you'd be dividing it by the area, it gets into the surface divided by the area, change in area, and then here's the big jump. These are all equivalent expressions, okay? Negative P dg dx minus q dg dy plus r, and we could technically, I guess, do dg dz, but this is back to the same idea where g is z, and it's a function of x. Well, here, let me write this a little bit differently. g of xy is z. Okay, so that dg dz would just be 1. Okay, and then dA. Okay, and let me define a little bit here. Where, first of all, that's true, and f is pi plus qj plus rk. Okay, so it's this dot product here, basically. Okay, oops, and I wrote dot instead of cross there. That'd be confusing. Okay, so some equivalent expressions that we will be using. Okay, let me get you an example of that. Oh, okay. This is also called flux. Okay, it's a rate at which stuff passes through the surface. Okay. All right, so that was kind of a lot. Let's take a look at an example. This is exercise 24 in your book. Okay, so we have this vector field defined by okay, and then S is the part of the cone. Z equals square root x squared plus y squared. Okay, so that's just your, again, your classic cone, Z equals R, right? However far up you are is also the distance you are from the origin. 45-degree angle to the side of the cone. Okay, between the planes, Z equals 1 and Z equals 3. And they do tell you it has a downward orientation. And this is just given in the problem. You didn't have to figure this out. Okay. It has a downward orientation, which means that when we take our integral, it's going to be negative. Okay. And I think they just ask you to find the flux. Okay. So we're going to go ahead and use this piece right here. Okay. In fact, I'm going to grab it. I don't know why I always try to do this and then it doesn't work, but let's see if I can do it. Take that. I'm going to put it down there. I think I did it. Stop now. Okay. All right. Okay, so we're going to use this equation. All right. So our F, okay, is, let's see here. Let's get a different color here. Here's P. Okay. Here's Q. And here's R. Okay. And then our surface, Z is the square root of x squared plus y squared. Okay. So take the derivative of that with respect to x. And we'll have 1/2 times x squared plus y squared to the negative 1/2 times 2x. Okay, so we'll have x over the square root of x squared plus y squared. All right, and then if we have dg dy, it'll be very similar, just be y over the square root of x squared plus y squared. Okay, so, and then the fact that we had downward orientation. So we're going to have negative integral over d. We'll talk about that in a minute. Negative p, so that's going to be positive x times dg dx, so x over the square root of x squared plus y squared, minus q, so plus y, times y over the square root of x squared plus y squared, plus r. Okay, so plus z cubed, but we can't throw in that other variable, right? So z cubed is going to just be the square root of x squared plus y squared cubed, dA. Okay, so now we need to figure out what our x and y are between. Okay, so let's go back up to the whole idea. It's this, we're concerned about this cone. Okay, so I'm gonna switch colors here. So this cone is this guy. Okay, just between 1 and 3. Okay, so we can think about this in our xy plane. What we've got is this ring, right? If we were project this piece of the cone that we have down to the xy plane, we'd have that circle with a radius of 1 and that circle with a radius of 3. Okay, we want to get the equations of those circles to get the limits of our integral, and that's where everything just kind of falls apart. Like, I don't want to do that, right? It's much easier if we do r is between 1 and 3, switching it to polar, right? And theta is between 0 and 2 pi. Okay, which then means that we have to switch r dr d theta. This is going to go, let's see, r is between 1 and 3, and theta is between 0 and 2 pi. We have to switch everything to be polar. Okay, where x equals r cosine theta, y equals r sine theta, z equals z, right? Your polar coordinates are actually cylindrical. X equals r cosine theta, y is r sine theta, z is still z. Okay, so it's not that hard to do though with this, okay, because we know that x squared plus y squared is r squared. So r squared, right? Square root of r squared cubed. That would just be an r cubed. And then what's going to work out here is that those just give you x squared plus y squared over the square root of x squared plus y squared. So we've got r squared over r, which is just r. So if we switch all this to polar, the x and the y piece here, when we put those together, again, they have a common denominator, so they just become x squared plus y squared over that square root. That's just r. This is, and then this piece here will be the square root of r squared, which is r cubed. Okay, so it actually worked out really nicely then, where we just have r plus r cubed. And then our r dr d theta. Okay, so we'll have, again, separable, right? Negative integral from 0 to 2 pi of d theta times the integral from 1 to 3. We'll distribute that r, so r squared plus r to the 4th dr. Okay, so we're going to have negative 2 pi, and then we'll have r cubed over 3, r to the 5th over 5 from 1 to 3. Okay, might get some big numbers here. Negative 2 pi. Let's see here. R cubed will have 27 over 3, so that's going to be 9. plus, oh, let's see here, 81, 243. 3 to the 4th is 81. Yeah, 243 minus 1/3 plus 1/5. I think I did that okay. All right. So let's see how quickly I can think today. 9 minus 1/3 plus 242 over 5. Oh, Mrs. Ware. Okay, let's see here. Common denominator of 15. 9 times 15 would be 90 plus 45, so 135 over 15 minus 5 over 15 plus 3 times 242 would be 6. 2, 726 over 15. I think so. All right, we're almost there. So negative 2 pi. Let's see, 130 plus 726 would be 856 over 15. Negative 1600, 1712 pi over 15. That's a negative up front. Negative 1712 pi over 15. Final answer there. Okay, and that's the last problem from this section. So there you go.